Well, hello everybody, and happy day after Earth Day. And so I'm going to talk today about trying to save the Earth from air pollution, global warming, energy insecurity. So we've been developing plans over the last 16 or 17 years now to transition the world to entirely clean renewable energy, which includes solar, but also some other technologies. And so I want to talk about these plans, but then also talk about how California is doing in the last couple years, and especially this year, on this transition. And so without further ado, I just want to first start. So the problems I see from my point of view are air pollution, which causes about 7.5 million premature deaths each year worldwide, including about 100,000 in the US and even 12,000 in California, mostly in developing countries. But that's costing the world in terms of statistical cost of life and morbidity on the order of $30 trillion per year already. Global warming is expected to cost that amount, $30 trillion per year, by 2050. And energy insecurity is a major problem. I mean, fossil fuels are limited resources. They will run out at some point. And we do need replacements. And that's one type of energy insecurity. There are several others. So these are all drastic problems that require immediate and drastic solutions. When I say immediate, we need an 80% transition away from fossil fuels and bioenergy fuels that are combustion fuels within 5 years, and 100% within 10. And if we don't do it by 2050, then it's really going to be a bigger problem. So what's the idea? It's electrification of everything that we can, and providing the electricity from clean renewable sources. So if you think of energy as these four major sectors: electricity, transportation, buildings, and industry. For transportation, we go primarily to battery electric vehicles, but some for long distance heavy aircraft and ships, maybe some hydrogen fuel cell electric vehicles. For buildings, go to electric heat pumps. For air and water heating, air conditioning, and this could be water heating and dishwashers and washing machines, and also dryers, could be heat pumps. Using electric induction cooktops, going to LED lights, more energy efficiency, more insulation, reducing energy use. For industry, we have many electric technologies for high temperature processes, including electric arc furnaces, induction furnaces, resistance furnaces, dielectric heaters, electron beam heaters, electric heat pumps as well. And we also have what's called fire bricks, which I'll talk about in a little bit. We need, by the way, so of course forgot the electricity part, which is providing the electricity with just onshore and offshore wind, solar photovoltaics on rooftops and in power plants, some concentrated solar, some geothermal electricity and geothermal heat, existing hydroelectricity for the most part, maybe tiny amounts of tidal wave power. So these are all clean renewable sources, no combustion, no air pollution, no greenhouse gas emissions during operation. So these are the sources that we propose to solve these problems. And we need storage because the wind doesn't always blow, sun doesn't always shine, obviously. So the main storage worldwide for electricity right now is hydroelectric power, conventional. Second largest is pumped hydroelectric. Batteries are growing, as I'll show you. We broke a record in California on Monday for batteries by a huge amount, and I'll talk about that. But also grid hydrogen storage, that's going to be a possibility. There's also compressed air storage, gravitational storage. There are a few other types of niche types of storage that may or may not grow. We also need storage for heat and cold, so hot water and cold water tanks. Those are the biggest kinds of heat and cold storage worldwide. But also thermal energy storage underground, in soil, in aquifers, and in water pits. So those are for seasonal heat storage. In Northern Europe, there's a lot, some in Canada as well. We also need storage for some hydrogen applications. We propose only green hydrogen, not from gas, not from anything else. Just green hydrogen, and used primarily for, there's ammonia production. You need hydrogen steel production to replace coke and coal for reducing iron ore to pure iron. I mentioned some long distance heavy transport and some grid electricity, but not for passenger vehicles, not for transporting to buildings for heating buildings, not for industrial heat. We don't need those. Much more efficient to use heat pumps and these other technologies I talked about. The next question is, can we power the entire world with just 100% clean renewable energy and storage for everything? And we think the answer is yes. So these are plans we just developed for 150 countries. We previously looked at 145 countries, 143 countries, 139 every year. We have additional data for additional countries. But these are the latest results. For 150 countries around the world, can we power the whole world? And these represent about 99.97% of all world emissions, by the way. So just to look at an aggregate, in 2022, the end-use power demand in all these countries worldwide was about 13.3 trillion watts, or terawatts. That's expected to go up to about 19.6 terawatts in a business-as-usual case by 2050. But the interesting thing is when we electrify and provide the electricity from clean renewable sources, our requirements for energy go down significantly, about 54%. And that's due to 5 major reasons. It's the efficiency of electric vehicles and some hydrogen fuel cell electric vehicles versus internal combustion engine vehicles. Worldwide, that's about a 20% reduction of power demand. Going to electrified industry reduces demand about 4%. Going to electric heating for electric heat pumps primarily, on average worldwide, we go down another 13%. And then 11% of all energy worldwide is used just to mine, transport, and refine fossil fuels and uranium. And so we eliminate that energy with a clean renewable energy world, and that saves about 11%. So, and then another 6.6% of end-use energy efficiency improvements beyond business as usual. That adds up to 54.2% before you even change your habits. And that's just due to electrification, and this is going to result in huge energy cost savings because we're just using a lot less energy with a clean renewable energy world. So this is kind of the timeline that, one timeline, the top line is if we don't do anything, that's a business as usual case, we go up to 19.6 terawatts worldwide end-use power demand. But if we electrify and provide the electricity from clean renewable sources, then our demand goes down those 5 shades of colors to the 100% WWS, wind, water, solar line, which is 9 terawatts. And then we provide that wind, water, solar with a combination of onshore and offshore wind, utility PV, CSP, solar heat, and some rooftop PV, geothermal electricity and heat, and hydroelectricity primarily. And that's a timeline, by the way, of 80% transition by 2030 and 100% by 2050. As I mentioned, though, we need to go faster. This is the same thing, but it just shows a faster timeline of 80% by 2030, 100% by 2035. If we can get 80% by 2030, we should be able to get 100% by 2035 because we actually have 97% of all the technologies we need to implement such a transition. We really need to deploy on a rapid, large scale to get this done. So just to give you the mix average worldwide, we did this for 150 different countries, but then this is the average worldwide of onshore wind would be about, this is just one mix. You can actually come up with multiple mixes. There are multiple solutions, and this results in keeping the grid stable, as I'll show in a second. Onshore wind's about 33%, offshore about 11%, rooftop PV about 15%, utility PV about 34%. The CSP is pretty small right now. Geothermal electricity about 1%. Hydro is about 4.5%, which is all existing hydro, by the way. And then small amounts of tidal wave and some heat. In the US, there's a list distribution as well. But just to give you an idea, we actually did grid stability analysis at 30-second resolution for multiple years worldwide for breaking the 150 countries into 29 world regions where we had set up grids that are interconnected grids. And we also did all 50 US states and some in isolation, including California. So this just shows an example of matching supply with demand and storage and demand response and for electricity, heat, cold, hydrogen, everything, keeping the grid stable every 30 seconds for multiple years. And I'm not going to go into the details of this, but we were able to solve this, keeping the grid stable everywhere in the world with just wind, water, solar. And storage. And you might wonder, well, what's the cost of keeping the grid stable? And I'll show you that in a second. But it's not rocket science. It's just an optimization problem to actually solve this. When people say, well, the wind doesn't always blow, the sun doesn't always shine, that doesn't matter. We can solve this problem. And I'll actually show you for California how California is actually doing that right now, today, as we speak. So let's look at what's the cost. The capital cost of keeping the grid stable worldwide among the 150 countries is about $60 trillion. US is about 6.5, China is about 15.5, Europe 5.4, California is $500 million to do this. But it'll turn out that the payback time is 6 years. The energy payback time, the social cost payback time is less than 1 year, and I'll show you how that's done. So the real relevant cost is the annual cost of energy, not the capital cost, not the cost per unit energy, but the annual cost of energy. in a business as usual case, well, today the world spends $11 trillion per year on energy, including all energy sectors. That's expected to go up to about $17 trillion per year in 2050. In 2050, we estimate the health cost will still be about $37 trillion per year from morbidities and mortalities and other health-related costs. The climate cost is expected to be about $33 trillion per year, so the total social cost in a business as usual case, if we do not do anything, is on the order of $87 trillion per year. That's not total, it's per year. If we electrify everything, provide the electricity with clean renewable energy, we eliminate the health and climate costs. These are associated with energy, by the way, the energy-related climate and health costs. There are other health and climate costs not associated with energy. If we will eliminate 100% of energy-related health and climate costs, if we go to wind, water, solar, we also reduce the energy demand, as I showed, by 54%, and the cost per unit energy by another 15%. So we get a total 61% reduction of the annual energy cost and a 92% reduction of the social cost. Just look at the energy cost savings. It's 17 trillion a year minus 7 trillion a year. That's 10 trillion a year savings. Divide the capital cost of 60 trillion by 10 trillion a year savings, you get 6-year payback time from the energy cost savings alone. And from the social cost savings, it's a payback time of less than 1 year. So, and you all know that solar and also wind and hydro are all cheaper than fossil fuels. IRENA has put out the world average cost, levelized cost of energy from fossil fuels, about $100 a megawatt hour. Utility PV is 44, onshore wind 33, offshore wind 75, geothermal 71, hydro 57. These are all from IRENA. They're less than fossil fuel costs for all these wind, water, solar technologies on the average worldwide. Of course, you'll find places where they're more expensive or less expensive. So how much land would this take? Well, on the world scale, we're not using new land for offshore wind, tidal, wave power. Rooftop PV does not take up new land. We're not adding any new hydro. We're using existing hydro. And geothermal is pretty small, so the main land is onshore wind spacing and the footprint from utility PV and CSP and some solar heat, which worldwide is about 0.39% of the world land for the spacing for wind turbines, and utility PV and CSP is about 0.18%, so a total of about 0.57% of world land. In the US, it's a little over 1%. In California, it's about 0.8%. But compare this, in the United States, 1.24% of all United States land area is used just to grow corn for ethanol to provide 4% of transportation energy. Just 4% of transportation energy, 1.24% of the entire US land area is used for that. On top of that, another 1.3% is occupied by the fossil fuel industry for their 3.2 million abandoned oil and gas wells, 1.2 million active oil and gas wells, millions of miles of pipelines, hundreds of thousands of gas stations, refineries, coal mines, etc. They occupy 1.3% of US land. So 2.5% of US land is occupied for energy right now. We would go down to around 1%. So there's actually a reduction of land use. Do not let anybody tell you that, oh, all that PV is taking up so much land. It's taking up way less land than other energy sources in the United States and also worldwide today. So what about California? You know, some numbers just for California. Similar thing, we'd reduce energy requirements to go, if we go to 100% renewables, by 60% versus a business as usual case. We'd reduce annual energy costs by 68%, reduce annual health costs by $134 billion a year and 10,000 lives saved per year, reduce annual climate costs to the world by $250 billion per year. The capital costs are about $500 million, but you save $129 billion a year in energy cost savings. So that's a payback time of 4 years in California for this. It'll create 220,000 more long-term full-time jobs than lost. Worldwide, we calculate 28 million long-term full-time jobs more produced than lost. And we require only about 0.34% of land for utility PV and 0.47% for wind in one particular scenario. Before I show you what's happening in California, I just want to talk about really briefly, it's one technology that's really cool, which are fire bricks for industry. Industry, people say, oh, it's a hard to abate sector for energy. Well, there's actually a new technology where if you, let's say, imagine you have 100% renewables, you can take that extra electricity from when you have too much solar, too much wind, and if you want to run an electric arc furnace or induction furnace 24/7, you need a lot of batteries, right, to store the electricity. The alternative is they're actually what are these high temperature bricks. You can actually produce heat that up to 2,000 degrees and store in these bricks. They're basically kiln bricks with slightly different compositions that store heat up to 2,000 degrees for multiple days. And you can run air through the channels in the bricks to provide heat on demand 24 hours a day. And you can actually then heat these bricks whenever you have extra wind or solar. And these are nice because they cost 1/10 the cost per unit energy kilowatt hour than a battery. And they're just made of dirt, basically. And they last for decades and decades because they don't break down. So I can't spend too much time on them, but I just want to say it's a really cool technology. There are companies commercializing them, and they can actually help solve they can provide heat for 90% of industrial processes. So you can eliminate arc furnaces, induction furnaces, resistance furnaces, dielectric heaters for most processes with these fire bricks, and they just heat by resistive heating inside the bricks themselves. Anyway, I don't have time to go into them more. Okay, so now let's look at what's going on in the world, what's actually happening and in the world in California. You might not have realized this, but there are actually 14 countries that produce 95 to 100% of all their electricity in the annual average with just wind, water, and solar. And there are several that are actually at 100%. Albania is 100% wind, water, solar. Bhutan, Central African Republic, Lesotho, Nepal, Iceland, South Georgia, and Sandwich Islands. They are all 100% wind, water, solar in the annual average in 2023. Ethiopia, Congo, Paraguay, Costa Rica, Norway, Namibia, Sierra Leone, they're also 95 to 100%. And they're dominated by hydro, of course, but some of them have solar, a lot of solar, some have a lot of wind as well. But what you might not realize is South Dakota in 2024 produced 118% of all the electricity it consumed with just wind, water, solar, with about 80% wind and about 35% hydro and 3% solar. And it also produced another 17% gas and 10% coal. So it produced a total number should be about 137% of its demand was produced, and it exported the excess. But the point is, it produced over 100% in the annual average of the electricity that it consumed with just wind, water, solar. And there are many other states that are very, very high too. Montana is over 90%, Iowa is 80%, Washington State 73%, Kansas 70%, Maine 68%, New Mexico 63%, etc. And many of these states are dominated by wind. Most of them are dominated by wind. 2 or 3 are dominated by hydro. And number 12 is California, which is the only one dominated by solar. And California is at 47 or under 50%, or last year it was. Now actually it's over 50%. But the really important thing here is of the top 11 that were all up between 15 to 118% of the electricity that they consumed from wind, water, solar, 10 of the 11 top states have electricity prices that are at least 1.5 cents per kilowatt hour less than the national average. So because you always hear, oh, renewables are driving up costs. It is just not true. In the United States, renewables are lowering the costs, and you can see that in all these states that are dominated by renewables, wind in particular, and also a lot of them have a lot of solar too, and hydro, they have among the lowest electricity prices in the United States. The only exception are Maine, and then the 12th one is California. And California's high price have nothing to do with the renewables. It has to do with the fires, the gas explosions, San Bruno, Aliso Canyon, the undergrounding, the strengthening of the gas lines underground. Now they're undergrounding transmission lines, and keeping Diablo Canyon Nuclear open it's costing huge amounts, and that's going to cost even more in the future. So it's transmission upgrades, it's fires that utilities have to pay that they just pass on to customers. Anyway, don't get me started with that. Okay, so let me just look more at California, and you want to see some really amazing, cool stuff. Let's start, this is last year. I'm going to show you a few slides of just daily what happens on a given day in California. So these slides on the left is the red line is the 100% of demand on California's main grid. Put this in perspective, California is the 5th largest economy in the world. And last year, there were 132 days of the year, California was over 100% wind, water, solar for part of the day. And this year, it's going to be close to double that. But I'm going to show it. This was a day where there was an eclipse. This was a solar eclipse. And the yellow here is solar production on the utility scale. This is not behind the meter, so this is not rooftop PV. This is just utility scale on the main grid, the CAISO grid, which is 82% of California's consumers are on the CAISO grid, including part of Nevada as well. But you can see, and the dark blue is batteries, the green is wind, the kind of orange is geothermal, and the light blue is hydro. And you can see when there was an eclipse, the batteries kicked in on the left to fill in the demand immediately. And on the right, you can see when there was the eclipse, the demand went up. And why did demand go up? Because there's so much rooftop solar in the in California, that when there's an eclipse, then suddenly there's much less rooftop solar supply, and people need grid electricity, need to pull electricity from the grid. So grid demand goes up because there's less rooftop solar available. So that's why the demand went up during the eclipse. But on this day, there was also over 100% renewables, as you can see, where some of the wind, water, and solar was above the red line on the left. That means you're over 100% renewables in terms of your supply. But, okay, so here's another day. This is where wind, water, solar met 162% of demand at its peak and exceeded demand for 10 hours during the day. And so that was last year. And this was also last year in May. 82.3% of the 24-hour demand was met during the day. But let's jump to this year, April 20th, which was a few days ago, Sunday. This was last Sunday. So wind, water, solar met 68% of the 24-hour demand and a peak of 155% of demand. Solar met up to 132% of demand. So there are actually many days this year, like at least 15 or so, that solar alone met over 100% of demand for part of the day in California, utility scale solar alone. And this is way higher than last year. And I'll show you statistics of this year versus last year in a second. But this one is Monday, where there's a new battery record set. So 9.72 gigawatts was the peak battery output on the grid in California on Monday. And that was 1.2 gigawatts higher than their last record. So in one fell swoop, California just added 1.2 gigawatts of batteries. And to put that in perspective, and that's 42.6 gigawatt hours. These are all 4-hour batteries. So 42.6 gigawatt hours of battery output during the day. That's 8.5% of the entire 24-hour electricity production in the state of California on the main grid was just from battery output. Of course, you had to charge the batteries from something, but my point is batteries are growing rapidly. This is 3 times the battery output available compared with just 2 years ago. So we've increased the batteries on the grid 3 times in just 2 years, which is incredible growth. Including solar has gone up a huge amount too, and I'll show you that in a sec. But there's also 38 straight days as of Monday. I haven't checked yesterday, I'm pretty sure it was also 100%, but 38 straight days of 100% wind, water, solar on the grid in California for part of the day, and the 79th of 111 days in 2025. And most of these are in winter, by the way. So there were many days in winter this year that solar alone was meeting over 100% of California's grid demand. So that's pretty incredible. So this shows the comparison of this year and last year. One interesting thing, demand has hardly changed this year versus last year, and demand in California is 4% less than 2 years ago. So despite the growth of data centers, AI, electric vehicles, crypto mining, all sorts of electricity demands, there's actually not much change, or in fact, there's a decrease compared to 2 years ago of the demand in California's grid. Why is that? That's because of the huge growth of rooftop solar, and that reduces grid demand, and I'll show you an example of that in a sec. But some other interesting things here. So wind, water, solar, just compared to last year, is up 11%, and compared to 2 years ago is up 19%. Solar alone is up 24% from last year, and is up about 54% from 2 years ago. So utility solar's increased 54% in just 2 years, from January 1st to April 21st, 25 versus 23. And wind is up 10% versus last year. Hydro is down 6%. Batteries are up 74% versus last year, but 200% versus 2 years ago. And fossil gas, this is a really interesting thing, is down 27% versus last year and 45% versus 2 years ago. So we've eliminated 45% of gas on California's grid in just 2 years. And that's going to it's going to keep going down. And imports are up 46%, but California is now importing more than 50% wind, water, solar, because all the states that it's importing from, most of them, except for Arizona and Utah, are all above 50% wind, water, solar in their production of electricity. So just here's some statistics. Here's the growth of the nameplate capacities of wind, water, solar generators in California through 2024. You can see the yellow is utility PV. The red is distributed or behind the meter PV. So you can see both rooftop PV and utility PV are growing really fast. Even wind is growing here. Batteries, though, are escalating, and they've grown even more in the last year. These are the nameplate capacities. So here's the demand thing. So the demand on the grid, like the purple line on the bottom, that's 2024 basically, or between 2023 and 24. And that's a drop during the day in particular compared with the previous year. So you can see that demand goes down because of the growth of rooftop PV that's reducing demand. And even last year when they changed the net metering law, you still got 80% of the previous year's growth of rooftop PV despite that change, which was good, but it's not as good as it could have been. Okay, and then just one more thing is, well, how can you get 100% wind, water, solar every hour of every day in California? Well, there's more utility PV and batteries, obviously. And just to give you perspective, in the queue in California, we have 35 gigawatts of utility PV and 34 gigawatts of batteries. So I said we have on the California CAISO grid, there's almost 10 gigawatts of batteries. There's another 34 gigawatts just in the queue that's people are ready to build if they get permission for it. So, and there's 35 gigawatts of solar, and there's like right now there's about the peak is around 21 gigawatts of solar right now. So there's another 35 on the queue just to be implemented. So we can go literally with just those two things. We can go 100% wind, water, solar every hour of every day if we just add what's in the queue in California. So you don't need all the rest of this, but rooftop PV and batteries, heat pumps, energy efficient buildings will help. Offshore wind, of course, that'll be delayed a bit, but there's a huge resource in California. Enhanced geothermal, in Utah, there's already an enhanced geothermal plant that's going to wield in 330 megawatts to Southern California. So that's another way to get more energy, and that's constant baseload energy. Shifting more hydro to night helps, and using demand response more effectively can shift the times of peak demand. Okay, so those are all ways to fill in the gaps. So just to summarize everything here, in terms of these large-scale plans for countries, we calculated, as I mentioned, 28 million more long-term full-time jobs than lost. We don't require a huge amount of land to transition. We'd avoid over 7 million air pollution deaths per year by transitioning the world. We'd reverse slower than reverse global warming. We can keep the grid stable throughout the world. Annual energy costs are about 61% lower than fossil fuel costs, and social costs are about 92% lower. And finally, if you want more information, here's lots of additional references and all the books. You know, all the plans are in published papers that are freely available. Certainly, if you want any of these documents, you can email me at jacobson@stanford.edu, and happy to send you any information that I talked about, including the slides. So thank you very much, and I hope you have a good conference. Thank you.
Thank you so much, Mark. And I think we have time for maybe one or two questions.
Okay.
And I see there's already one here. But great to hear that the technology exists, and it seems to be more of an optimization problem overall.
Yeah.
But perhaps if you could answer this first question that has come up here, is that we install new technologies in an outdated grid. How can we solve for a grid that is not keeping up with technology? What type of infrastructure investments?
Well, so yeah, one way to solve the problem is like wheeled energy from far away to close with more transmission. So you can either have lots of transmission interconnecting states, for example, or you can have a lot of storage, local storage, and less transmission. And so, you know, there's an extreme is like 100% storage, the other extreme is 100% transmission. But it looks like storage is winning that. So we're going to have a lot more storage and local production and less long-distance transmission, less new transmission. I think we can upgrade existing lines easier. I mean, it's all a question of speed. How fast can we upgrade transmission versus implementing new technologies? And we don't have a lot of time. And so I think we're going to have to rely a lot more on local production. This is why offshore wind in California is really helpful. We don't need much transmission for offshore wind. More local solar, more behind-the-meter solar. That helps a lot. But to answer the question, transmission is like a zoning issue partly, and it's partly getting approvals and getting permits, and so there's a lot of potential for delays. So I don't know if I have the answer to that, but I think, yeah, we've got to rely a lot on local production and storage, I think.
Thank you. And I'm not sure if in part of your study updated research, if you look into the need and if whether your plan accounts for the additional need.
America alone, just in central North America, there are 50,000 new oil and gas wells drilled every year. So when we're talking about the amount of lithium we would need to run all battery electric vehicles and grid storage, we're talking about a few tens of mines, not tens of thousands every year. And so we're talking about orders of magnitude, at least 2 to 3 orders of magnitude less mining for the entire wind, water, solar infrastructure. And of course, we want to avoid mining as much as possible. So certainly recycling, there are companies that recycle batteries, or companies recycle solar now. That will help to, it's going to be hopefully be one-time mining, and then we can recycle the resources for future use. But I'd say it's just a lot less mining than we need in the current energy infrastructure.
I would expect. And I see other questions popping up, but I would invite attendees to come find you during the break and maybe try to ask these questions in person so that we are able to finalize this session. But great to have seen real life numbers and a few of the scenarios and projections that you've created. And thank you so much for opening the conference today.
All right, thank you. Thank you. Thank you.